In today's lecture, Probability 1, we'll be looking at some simple probability basics that we apply to genetics. Two things we're going to talk about are one, the multiplication rule and the addition rule, describe what they are and how they apply to genetics. The second thing we'd like to do is apply the probability method to conduct a monohybrid cross and describe a series of events. Whenever you talk about applying probability to genetics, you really want to know the rules, just as if you were going to go to Las Vegas. You want to know the rules of the game. And so with probability, if we're talking about rolling a die, which is a very common example, there's 6 sides to a die, right? 1, 2, 3, 4, 5, 6. The probability of rolling any one of those individual numbers is 1/6. So in other words, the probability of rolling a 1 is 1/6. The probability of rolling a 2 is also 1/6. 3 is 1/6. I think you get the idea. So if we look at a single event, in other words, rolling a 1, 2, 3, 4, 5, 6, any of those individual events, the probability of any one of those happening is 1/6. So it's very, very basic. When we talk about a series of events, things get a little more tricky. And this is where we have to discuss the rules of probability a little bit further. The first rule is called the multiplication rule. And what the multiplication rule is let's ask a question like this, for example. What is the probability of rolling a 2 on your first roll and then a 3 on your second roll? The key word is and. So let's look at that. So let's look at the 2. We roll a 2. The probability of that is 1/6. Let's just consider a 3. The probability of rolling that is 1/6. So again, each individual rule is not an issue, right? 1/6 to roll a 2, 1/6 to roll a 3. But if we're looking at a series of events, the probability of rolling a 2 on your first roll and then a 3 on your second roll. Keyword is and. If you find yourself saying and, whenever you want to look at those two events happening in a series, you have to multiply the probability of each individual event. So it's called the multiplication rule. If we multiply 1/6 times 1/6, the answer is 1/36. So the answer to this question is 1/36. And basically what you're saying here is you want to look at your answer and say, does it make sense? Because there's another rule we'll talk about in a second called the addition rule. If the multiplication rule makes sense, then our answer should make sense. In other words, if we multiply these two, we get 1/36, which is much, much lower than any of these individual events happening. So when you do the multiplication rule, you should expect that your answer will be lower or more difficult to achieve than any individual event. And then you know your answer at least makes sense. At least you're going in the right direction. So in other words, is it harder to roll just a 2, which is 1/6? Or is it harder to roll a 2 and then a 3? Obviously, it's harder to have those two things happen back to back. And so 1/36 is a lower number. It makes sense at least. The second rule we want to talk about is the addition rule. With the addition rule, such as a question like this, what is the probability of rolling either a 2 or a 3 on your first roll? Well, the probability of rolling a 2 on the first roll is 1/6. The probability of rolling a 3 is 1/6. If I say either a 2 or a 3 on the first roll, basically what I'm saying is if I say either or, I'm using the addition rule. I'm going to add these numbers. When you're adding fractions, remember you add the numerator, the top number, but the denominator stays constant. So 1/6 plus 1/6 equals 2/6. Sometimes you want to simplify, so if we simplified that, it would be 1/3. So that's how you do the addition rule. Again, we want to look at it and say, does it make sense? If we do the addition rule, the answer to our question should be more probable than any individual event happening. In other words, ask yourself, is it harder to roll just a 2 on the first roll? It's 1/6 probability, right? Or is it harder to say I can roll a 2 or a 3? Obviously, you're including more events that can happen, right, to satisfy the condition of this question. So rolling a 2 or a 3, either one of those together, that's much easier to achieve than rolling either of those individually. So individually they're 1/6, but if you say, we could do this or this, we have to add the two of them, and this is a more likely event that will happen in our answer. So let's try a couple questions. So you might say to yourself, okay, what's the probability I'll have 5 children and each of those children be a Packers fan? You want to say, which rule would you use? Now, I'm a Bears fan, so if you're from Chicago or Green Bay, you know that it's a nice rivalry there. So what else would you be if you're a football fan? Either going to be a Bears fan or a Packers fan. Let's say that's all that exists. Those are the only two options. So the question is, okay, what rule should I use? So each child has a chance of being a Bears fan or a Packers fan. If I'm saying I'll have 5 children, each of them will be Packers fans, I'm saying the first child will be a Packers fan, and the second child, and the third, and the fourth, and the fifth. Notice emphasis on the word and, so I'm using the multiplication rule. So how exactly would I do that then? Well, I'd say the probability of the first child being a Packer fan is 1/2, because either they could be a Packer fan or a Bear fan. That's it, right? We're excluding all the other NFL teams, obviously. So the first child, it's 1/2 chance. The second child, it's 1/2. The third is 1/2. The fourth, the fifth. I'm multiplying all those down the line using the multiplication rule, and my answer will be 1/32. So the answer to this question is 1/32. Again, ask yourself, does it make sense? Well, any individual child being a Packers fan is 1/2. If I'm saying I need 5 in a row to all be Packers fans, that's much more difficult, right, than having just the first child. So the answer should be much lower than any of the components in the problem. Okay, so let's apply these probability rules to genetics itself. So let's look at a cross when we talk about albinism. We referred to this in some of the transmission genetics lectures. So there's 2 alleles for albinism in humans. There's big A, which is normal pigmentation. There's little a, which encodes for albinism. Remember, big A is dominant to little a. So if you're a heterozygote, you're a carrier for albinism, but you don't express it, right? Because the big A dominates the little a. Let's consider this cross over here. We go ahead and do that cross. We get those ratios. Remember, great genetics, please, ooh. And then you'll notice that, okay, so 1/4 will be big A, 1/2 will be big A, little a, 1/4 will be little a, little a. Now we're really interested in the phenotypes, right? When we're talking about probability, we're saying, you know, is the child going to be normal or have albinism? And then look at sequences. So we don't care about the genotypes per se, although they're very important, obviously, but we care about the phenotypes. So if we look at that, these first 2 individuals will be normal, right? Big A, and big A, little a. So 3/4 of the population will be normal, or I should say, every time this couple has a child, there's a 3/4 chance that the child will be normal, and then there's a 1/4 chance that the child will express albinism. So let's practice. Let's apply this to different probability problems. Then, considering this cross, just to put that info up there from the last slide, just so we remember that, let's go ahead and apply this. So let's ask this question. What is the probability of these parents having a child who is either heterozygous or homozygous recessive? So if we're saying heterozygous or homozygous recessive, we're saying heterozygous or homozygous recessive. You might say, why would you ask such a question? Well, the homozygous recessive individuals will be affected by albinism, and the heterozygotes will be carriers. So you could see that the big A does not express albinism, and that person cannot possibly pass it on to their children. So that's why you could maybe ask this question, to see what individuals are affected or which individuals have the capability of passing albinism onto their children. So let's look at this problem. So, okay, child number 1 could be big A, little a, right? Could be heterozygous. There's a 1/2 chance that that's possible, right? 1/2, that's where we get it from. Child number 1, so same child, right? Theoretically, could be little a, 1/4 chance of that. Then I got to think to myself, what do I do here? I'm saying the child is either big A, little a, or little a, either or. I'm using the addition rule. So I go ahead and add those, but when I'm adding them, keep in mind, when you add fractions, the denominator has to have the same number. So 1/2, 2 is not the same as 4, so we got to change that. If we change it, 1/2 really is the same thing as saying 2/4. Now we can go ahead and add 2/4 plus 1/4. If we do that, whenever you add fractions, whenever you add the numerators, so 2 plus 1 is 3, and then the denominator stays constant. So the answer that you get for this problem is 3/4. That's how you apply the addition rule. Let's ask another question. Again, applying the same principles that we learned, but let's look at the multiplication rule this time. So same problem, but multiplication rule. Here's a new question. What's the probability of these parents having 3 albino children? In this question, the only number we really care about is this one here. Each individual child has a 1/4 chance of being albino. So what that means is we're saying if they're going to have 3 albino children in a row, what we're saying is the first child is going to be albino, 1/4. The second child is going to be albino, 1/4. And the third child is going to be albino, 1/4. So So I'm saying child 1 is albino, and that's where the multiplication comes in. The second child is going to be albino, and the third child is going to be albino. When you multiply fractions, you just multiply the numerator across. So 1 times 1 times 1 is 1, and then you multiply the denominator across. 4 times 4 is 16, times 4 is 64. So the answer to this is 1 over 64. Again, ask yourself, does it make sense? And it does, because it's harder to have 3 children being albino, right, 164, than having a given child be albino, which is just 1 over 4. Let's apply the multiplication rule. Again, same general situation, right? But, slightly different question. What if we said, what is the probability of these parents having their first child be albino and their second and third children be normal or have normal pigmentation? Notice I'm using and again. So same rules apply, just different fractions, right? So the first child's albino, that's 1/4. And, so I'm multiplying, the second child is going to have normal pigmentation. In this case, it's 3/4. Again, I got the 3/4 from right up here. And the third child is going to be normal, that's also 3/4. So if I multiply the numerator across, 1 times 3 times 3 is 9, and then 4 times 4 is 16, times 4 is 64. So 9/64. Again, ask yourself, is this less likely than any of these given situations? And of course it is, because it's a smaller fraction. So those are the rules that we wanted to go over today in this Probability 1 lecture. We looked at the multiplication rule, the addition rule, and we talked about probability method, how to conduct a monohybrid cross, and then a series of events. In our second lecture on probability, we'll talk about slightly more complicated situations where we use the multiplication rule and the addition rule in the same problem. We'll also talk about applying probability to dihybrid crosses, as well as using something called the branching method.